Hello, this is Dr. Baxley. Here's a quick answer key for the practice quiz for unit number 1 with significant figures, conversions, and scientific notation. This number has 3 significant figures because trailing zeros after a decimal point are significant. The next number also has 3 significant figures. The beginning zeros aren't significant, they're just placeholders, but these were measured values. The next number follows that same rule. Zeros in between numbers are significant. Trailing zeros after a decimal are significant. So this has 5 significant digits. 10 pies you might think would be an ambiguous number, but we're pretty sure we can count up to 10 pies pretty accurately. It's not 10.1 pies or 9.99 pies, so this is going to be an exact number. It wouldn't limit the number of significant figures. In scientific notation, this would be 201641 with a decimal place right after the 2. This would be times 10 to the 3 in terms of grams. The next question would be 5.90 times 10 to the minus 4 meters. For calculating answers to the correct significant figures, if you add all of these numbers up together, you get 161.1 for what's in the parentheses. Divide that by the 3222. That works out to be 0.05000 to 4 significant figures. Why 4? When the numbers here only had 3? Well, when they add together, we get an extra significant digit because they add up to over 100. The next problem is similar. Doing the subtraction first in the parentheses yields 0.05038, where the 3 is the last significant digit. That value is squared, and then subtract from that the 0.00050. The squared term works out to be 0.002538 to 3 significant figures. Subtract from it the 0.00050, and that works out to be 0.00204 to the last known digit. In converting metric units, in terms of converting from nanometers to kilometers, I don't know a direct conversion from nanometers to kilometers. So I'll do the nanometers to meters first. And once I've done the first conversion, then I can convert to kilometers. And that should be 1.18 times 10 to the 5th kilometers. For the next problem, it's gigawatts to milliwatts. Again, I don't know a direct conversion, so I'll start by converting gigawatts to watts. Once I know the number of watts, I can convert to milliwatts. And that should give an answer of 1.7 times 10 to the 7th milliwatts. For milliliters to gallons, I'll need to look up a conversion from some metric unit to gallons. And I can find in the table in Unit 1 in the lecture notes that 1 gallon is equal to 3.785 liters. So I'll need to use that conversion. I think what I'll do is do milliliters to liters first, and then liters to gallons. So here's the worked out solution. Notice that I've used the conversion of 1,000 milliliters for every 1 liter. It's just like some of the other conversions we've done, except usually we would have done 1 times 10 to the minus 3 liters for every 1 milliliter, following the table from Unit 1. But we can multiply the numerator and the denominator by 1,000, and this is a very common conversion factor you'll see for the metric prefixes. That works out to be 0.531 gallons. The next problem is one of the dreaded word problems. I have several tips for word problems, one of which is to always look for a measured value that's not a ratio if you can find one to use in the problem. So if we look at these, there's a ratio of 0.95 meters per second, but then there's a measured value of 2.9 feet. So starting with the 2.9 feet might be the best way to go. I can start from feet, and then maybe I can calculate inches. I need to get to meters eventually, so maybe from inches I can calculate centimeters from the 1 English to metric conversion you're supposed to know. From centimeters, then I can calculate meters. And then maybe I can use this ratio of meters per second to calculate how long it'll take for the nerve signal to transfer. So let's start with the 2.9 feet. Convert that to inches, and then to centimeters, and then to meters. So here I've got feet turned into inches. I've got inches converted to centimeters, and centimeters converted to meters. Now I can use this ratio of 0.95 meters for every 1 second for the nerve signal, and I can convert seconds to microseconds. And that should give an answer of 9.3 times 10 to the 5th microseconds. I actually looked this stuff up, and so it does take about a full second for a nerve impulse to go from your finger to your brain to tell you to stop touching something hot. Here's the last question on the practice quiz. It's got some crazy units in it that we haven't dealt with. Again, I encourage students to try to find a measured value that's not a ratio to start a problem with. In this particular case, if you look at the ice cream, we know that the person's eating 115 grams of the ice cream. And who eats just half a cup? I sure can't. We do have a couple of ratios. We have 225 kilocalories per hour, and we also have 165 kilocalories per 70 grams of the vanilla ice cream. So maybe I can take the mass of the ice cream and convert that to kcals, and then from kcals I can convert that to hours, and then maybe then to minutes. So I'll start with that measured value, 115 grams. I can use the ratio of 165 kcals per 70.0 grams of the serving of ice cream, and then I can use the ratio of kcals per hour, and then a conversion you probably know, 60 minutes per hour, to calculate that this would be 72.2 minutes of a well-deserved walk after you ate merely a half a cup of ice cream. That's it for the practice quiz. I hope you did pretty well. If you have questions, let me know.